Welcome to a new section. Today we are going to study electric field at a point on the axis of uniformly charged ring. For that, consider a ring of radius A. We are considering the total charge of this ring is Q and is distributed uniformly over its length. Let's mark this center as O. Now we have to find the electric field at point P, distance R away from the center, and it is on the axis of the uniformly charged ring. For that, we are going to consider a small element dl here, which consists of a small charge dq. Let us mark this point, that is A. Now you can join the points A and P, which is the distance from this small element dq to the point P. We already studied we can calculate the electric field at a point due to a continuous charge distribution like this by finding the electric field due to this small element and then integrating within the limits to get the total or net electric field at that point. So we are going to calculate the electric field at point P due to this small charge dq. We are going to take it as dE, and we know it is in this direction. We can divide this electric field dE into two components. One is along the axis and the second is perpendicular to the axis. The component along the axis is dE cos theta if this angle is theta, and the component perpendicular to the axis is dE sin theta. Now for understanding the case here, just consider a small element dl that is same as that we considered here, which is having the same charge dq. Then the electric field at point P due to this small charge dq is dE, which will be same as that of this one, but in this direction, because the distance AP will be equal to this, and we can divide this into two components. One will be d cos theta, because we know this angle will also be theta, and we will get another component perpendicular to the axis, which is dE sin theta. You can see, due to this symmetry, that is, if you are considering a small element here, we can consider the same element just opposite. In this case, the perpendicular components, that is sin theta components, will be opposite to each other and they will be cancelled. So due to this symmetry, the perpendicular components will cancel each other and components along the axis will add up. That is, the parallel component, that is d cos theta, will add up due to each element. So we only need to calculate d cos theta and then integrate it within limits to get the electric field at this point P due to the uniformly charged ring. So our aim now is to find d cos theta and then to integrate it within the limits to get the electric field at a point P due to this uniformly charged ring, and the direction will be along the axis of the ring. So what is DE? DE is the magnitude of this electric field at point P due to this small charge dq, that is equal to 1 by 4 pi epsilon 0 into the point charge, that is dq divided by distance square. Here the distance between the point charge to the point P is AP. So AP square. So we got DE. Now our aim is to find cos theta. We know this angle is theta. Therefore this will also theta. Therefore cos theta is equal to R divided by AP. So we got DE cos theta is equal to 1 by 4 pi epsilon 0 dq divided by AP square into R divided by AP. So that is equal to 1 by 4 pi epsilon 0 R dq divided by AP cube. Now what is AP? If this is A, that is the radius, and this is R, that is the distance from the center to the point P, then AP is equal to square root of R square plus S square. So if we find AP cube, it is equal to R square plus A square the whole raised to 3 by 2. So this equation can be written as 1 by 4 pi epsilon 0 R dq divided by R square plus A square the whole raised to 3 by 2. So we got d cos theta, that is the parallel component of electric field at point P due to this small charge dq, which is equal to 1 by 4 pi epsilon 0 R dq divided by R square plus A square the whole raised to 3 by 2. Now our aim is to find the electric field due to the whole ring. For that we need to integrate this value. So the magnitude of electric field E is an integral of this value, that is 1 by 4 pi epsilon 0 R dq divided by r square plus a square the whole raised to 3 by 2. We know 1 by 4 pi epsilon 0 is a constant. R is the distance from the center of the ring to the point P. It is also a constant here. A, the radius of the ring, that is also constant. So we can take the constants outside. So the equation becomes 1 by 4 pi epsilon 0 r divided by r square plus a square the whole raised to 3 by 2 into integral dq. We know dq is the small charge in that small element dl. So if you are integrating dq, we will get the whole charge of the ring. The whole charge of the ring, we already taken it as q. Therefore, if you are integrating dq, we will get the total charge of the ring, and that is equal to q. So this equation becomes 1 by 4 pi epsilon 0 r divided by r square plus a square the whole raised to 3 by 2 into q. So we got electric field at a point on the axis of a uniformly charged ring is equal to 1 by 4 pi epsilon 0 r cube divided by r square plus a square the whole raised to 3 by 2. And we know the direction is along the axis because the parallel components are added up and perpendicular components will cancel off. So we got the electric field at a point due to a uniformly charged ring. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.